This room-sized machine can power an entire city by unlocking the energy inside atoms. Before you learn how to build a nuclear reactor, what is nuclear fission? Here's a heavy atom of uranium. Most of its energy is stored in its nucleus as nuclear energy. In nuclear fission, we use a neutron to split the nucleus. The released nuclear energy flings the two halves of the nucleus apart 10,000 times faster than a bullet, like cutting a powerful elastic band. Now at human scales, a single fission is barely noticeable. But 2 or 3 neutrons are also released, which can split other nuclei which release more neutrons in a violent chain reaction. In 1/1,000,000th of a second, a ball of uranium the size of a grapefruit releases enough nuclear energy to destroy an entire city. But if released gradually, it can power a city. So, how do you build a nuclear reactor? We start with our nuclear fuel, uranium dioxide. Only about 4% of the uranium can undergo fission, with the rest used in step 2. The fuel is made into finger-sized pellets, which are stacked inside long rods, which are bundled into arrays, which are packed into the reactor core. About 100 tons of uranium in total. To block the deadly nuclear radiation, the core is surrounded by thick steel, which is then surrounded by thick concrete. So now, how do we start our reactor? Startup neutrons are needed to ignite the reaction until it can sustain itself, much like lighting a candle. In small research reactors, a radioactive neutron source is used to ignite the reaction. But in commercial reactors, the uranium-238 in the fuel experiences tiny levels of random spontaneous fission. Although tiny, this provides the startup neutrons for the fuel to ignite itself. But there's a problem. Fission neutrons are too fast to be caught by uranium nuclei, the equivalent of catching a basketball moving 100 times faster than a bullet. This means the reaction quickly dies out. Only by making them 9,000 times slower can they be caught by nuclei and trigger fission. So, how do we slow the neutrons down? Each time a neutron collides with a similar mass particle, it loses energy and slows down. Protons have a similar mass to neutrons, and because water contains 2 protons per molecule, it's the perfect choice for slowing down neutrons. The reactor core is filled with water, which slows the neutrons enough to trigger more fission. But with each fission producing more than one additional fission, we have exponential growth, a supercritical reaction. Like a wildfire, the reaction could grow into a nuclear meltdown. So, how do we control our reaction? Boron-10 is great at absorbing neutrons. When the reaction is too fast, boron control rods are inserted between the fuel rods, removing neutrons and slowing the reaction. And when the reaction is too slow, the rods are retracted to allow more neutrons and speed up the reaction. So now we have a working core, the size of a small room, while producing the heat energy of a small volcano. But how do we turn this heat energy into useful electricity? The water in the core used to slow down neutrons is also used to transfer heat energy. In the primary loop, an Olympic swimming pool's worth of water is pumped through the tiny core every 3 minutes. The water is heated to about 330 degrees C, and to avoid boiling, the primary loop is highly pressurised. The primary loop then heats a secondary steam loop via a heat exchanger. A turbine converts the steam into rotation, and a generator converts the rotation into electricity. A single reactor can power 1 million homes, an entire city. Finally, a third condenser loop uses cold water to turn the steam back into water, often requiring large cooling towers, rivers, or the sea. So that's how to build a working nuclear fission reactor. But a final question: where does this incredible nuclear energy actually come from? If you weighed the fuel rods before and after 1 year of use, there would be 1 kilogram of mass missing. Where's this mass gone? Well, according to E equals mc squared, 1 kilogram of mass is equivalent to a huge amount of energy, 90 petajoules of energy to be exact, about 1,500 Hiroshima bombs, released gradually over 1 year. Please like and subscribe for more science videos.